Hello again. Tonight we're going to talk about quantifying radiation reflection pressure. This is part one of hopefully a two-parter at most. Didn't quite get everything done this week, but I got a lot of the principles and math and process and things like that done. Didn't get the actual observations done, but hopefully in the coming week. And as I said, another two-parter. I'll just leave that slide up for a few seconds in case people want to see how my week went. So the idea behind this is I've played with the concept of radiation reflection pressure, basically photons transferring their momentum onto a reflective surface. Think of it as a more optimized version of a solar sail, more intentful as to the photons being emitted and reflected. And I said, I need to measure that. I need to measure that force. But the force is so tiny that you need all kinds of special equipment in order to measure, nano-Newton level forces. And I've just not got the budget or the environment to build those sorts of things. So I said, maybe there's another way I can do this. The goal is just to confirm that there is a force and it's measurable, and that it's specifically what I intended to be and not, a side effect like heat, infrared heat in the wires or something. So here's how I connected the dots. There are these things called micro electrical mechanical systems, or MEMS, and they use them with microphones. The little tiny hole you'll see in your mobile phone or your tablet or computer, that little tiny hole has a chip behind it. And that chip is a composite circuit. It has a little tiny piece of crystalline zinc oxide material as a piezoelectric, which means when something strikes it, it makes an electrical signal, and as voice creates essentially a shock wave in the air from the vibrations, it energizes the piezoelectric material and produces a voltage that then gets amplified, filtered, converted into a digital signal, and now you can measure audio, microphone audio, as essentially a digital value. And so I said, well, if it can measure impact forces, then maybe I can use that to measure the flux of photons striking that same piezoelectric material. But in order to rule out that it's not some side effect of heat, I'll have to do this in a vacuum chamber. Luckily, I have a 5-gallon vacuum chamber. It has a nice clear lid on the top so I can shoot video down into it. But I need to be able to adjust this. So I need a computer to control it. I need an LED that I can adjust the color intensity on, and I need the MEMS microphone, get the digital signal from that, process it. So there's a lot of stuff to set up that the average person's not going to do, but a do-it-yourselfer might consider it if it was easy enough to do. So that's what this video is about, is showing you maybe it's easier than, hiring out the NASA Glenn Center in Ohio to measure your nano-Newton scale force. So this little piezo MEMS microphone, it has an interface called integrated circuit sound, or I2S. It produces 24-bit audio data, like sound system, and it puts it in a 32-bit data frame, and it sends those periodically. And the minimum amount of pressure that will activate the detection and measuring is 26 decibels, plus or minus 3. A decibel is a unit of acoustic force, and it presumes that you have an air pressure. It presumes 94 dBs of air pressure, and we won't have that in a vacuum. So there's some math to think about for that. But the way it converts the electrical voltage into a digital signal is by use of an analog to digital converter. And it does this over a range from 20 times a second, 20 hertz, up to 10,000 times a second, or 10 kilohertz. And it does this on a 44.1 kilohertz audio stream, which is, normal audio on a computer, 44 kilohertz. It's a very noise-free processing system, 94 decibels. It's a single microphone, so it doesn't do stereo. If you want to do stereo, you get 2 chips. And I was thinking that if the photons impacting the piezoelectric chip in the microphone were of different wavelengths, different colors, with a difference in force based upon the difference in wavelength allow me to measure a difference. Would it be detectable at all? And if so, could I discern basically what color I'm sending to it based upon the wavelength of the photons? So it starts getting tricky very early on. You have to understand certain units of measure. There are international standards for units of measure for things like force, pressure. And so that's where you get in things like newtons, which is a newton is 1 joule. That's 1 kilometer squared per second squared. And that's like a continuous force. And then if you want to measure it as an energy, you can measure that in its equivalent, which is a joule. Two different names for the same basic unit of measurement. But when you're doing it as an air pressure, like wind hitting the microphone kind of thing, then you measure that not in newtons, but in pascals. And 1 Pascal equals 1 Newton-meter squared. So it's a pressure force over an area. If we have a force from the photons hitting the piezoelectric material, and we have a microphone that measures acoustic waves in decibels, we have to know whether or not it's going to be sensitive enough to pick it up at all. So we have to convert pascals, that unit of air pressure force, to decibels, the unit of energy on the sensor. And there's some math for that. The sound pressure level, or SPL, is 20 times the log of a ratio. The ratio is the reflection pressure in pascals and the reference pressure. That's kind of like your atmospheric pressure. But since we're doing this at a vacuum, that's essentially 0. Oh, look, a divide by 0. Turns out that would essentially be an infinite value mathematically off the scale. And the log of infinity is infinity. So it's 20 times infinity, which is still infinity. So this particular parameter has no effect on it. But it was just curious to see that when you drop the sound pressure down low enough, you don't run off the bottom end of the detector, of the microphone, of the amplifier. You run off the math as you get to 0. So my pressure chamber, I can adjust the pressure on it. And if I want to try it from other than complete vacuum, I can do that. So a characteristic of reflection pressure is that you can actually take the wavelength of the photons and come away with what would be the force, the amount of momentum transferred in joules. And remember, joules and newtons are pretty much the same. So the calculation would be the force in joules from the photons hitting the surface of the piezoelectric material, not the voltage output, but the actual just force upon the piezoelectric is the Planck constant in joules per second. So you can see that the joules with joules drops away, and the speed of light, and then the wavelength of the photons in meters. Most of the time you get the wavelength of colors in nanometers or billionths of a meter. So there's some ratio that has to be done there. In our case, we're going to be expressing this as a force upon the piezoelectric sensor that's the microphone input port. And that's going to generate our electrical voltage. Now we get down to the very, very, very small numbers. You can calculate based upon the wavelength or the color of light what the force in joules would be. And this is for a single photon. And there's many millions to billions of photons from a light source. Don't think of it as it's just way too small a number, because it's actually going to get even smaller. But times 10 to the minus 28, that's pretty much nothing. And that's the same opinion that people had when they came up with ion propulsion for deep space and satellite use. And now it's a satellite orbiting the Earth would not use anything other than ion propulsion or some other experimental form of propulsion, because you'd run out of rocket fuel. Well, with ion propulsion, you can get a very small number of newtons of force, usually on the order of under 20 millinewtons or thousandths of a newton. And that works just fine to keep the satellites in orbit for years. Small may be small, but if it's something you can add up, then it's not so small. But when the photons hit the piezoelectric material, if the material is not reflective at all, then you lose some of that force. It gets absorbed. And if the photons come in at an angle, that also changes the amount of force. So in this case, we've got a hole that the photons go in and hit the piezoelectric material at 90 degrees. So very little effect on it, but it does bump it up to times 10 to the minus 60-ish. And you can see that the numbers change based upon red, green, and blue wavelengths. But remember, this is just for one photon. So we're doing this in a vacuum chamber. We have to convert the Pascals of force to decibels to be able to measure the electrical output of our piezoelectric material. And so we need to know how big the little piece of zinc oxide is. And it's very, very tiny. It's 0.325 millimeters in diameter. So from that, you can calculate the area of a circle. And then given that you're not going to be using the pressure at zero, it's essentially 2 times the number of pascals is the resultant force value that's going to be producing your voltage. And so I calculated those out, and it came out to be something times 10 to the minus 66, which is infinitesimally small. But remember, single photon. But if you were to look at our photon emitter, this is a thing called a NeoPixel, and you can send data to it and say, I want to activate the red, green, or blue, or a mix at certain amplitudes, certain brightnesses. You can turn all 3 channels on at once if you want to, but the amount of light output is different based upon it being the red, green, or blue channel, because they try and divide up the energy, the power going to each of the 3 LED chips pretty much the same, but that means that the amount of light you're getting out of it is going to vary based upon the material. So you can see that you've got the NM, the Newton meters. Oh, look, there's an error there. It should be NM on that blue, not MM. That's millimeters. That's wrong. But the next column over is millicandela. A candela is an SI unit associated with irradiance, basically light energy. And then you have the last number column, which is lumens, which is a value of irradiance based upon human eye perception, which is why it's so much larger in the green range, because that's where the human eye is sensitive, is in the green range. But that's the total amount of energy coming out of this 3-channel light source. So now that you know how much energy is coming out on a per channel basis for this chip, and the total amount of energy produced by the chip is 1/10 of a watt. So now we can calculate what the number of photons per second, the total number of photons per second would be. And then from that, we can sum it up and come away with the total decibels from our light source. And you can see we went from minus 60 something per photon. So you can see the number down in there. Hey, look, it took a huge jump up because there's so many photons being generated per second. 8.87 times 10 to the plus 16. That's a fairly large number. And you can see how the green is biased. It's got plus 17, it's a little more. But the decibels are still times 10 to the minus 49, which is very low. But this is for a 1/10 of a watt LED. They do make 4-watt LEDs. You can multiply the dB values. So how do we correlate this stuff hitting the sensor and making what it thinks is sound, but it's actually just a voltage, and we can measure that? We're not going to be measuring the frequency of the light directly. We're not going to be like taking in a photon and measuring its wavelength. It's going to be based upon the photons hitting it and how many of them are there. It will change the amplitude of the signal. And when we change the color and we change the flux, the number of photons hitting it, now we can see a hopefully difference in amplitude. This one is something that I actually pulled from the world of LiDAR and radar. So when a police officer is measuring the speed of your excessively traveling fast vehicle and he points the radar gun at you, how does the radar gun know that the radio signal that's sent out that bounces off your front bumper is actually from his radar gun? Because when his radar gun sends the radar signal out, the radio signal, it actually modulates it or encodes essentially data in the signal. And then when it bounces off your vehicle and comes back to the radar gun, they can decode that data and go, well, this is my data that I sent out coming back. It's not like some stray radio frequencies. And we're doing the same thing here. when the photons are sent out, they can be modulated or switched on and off in certain patterns, and that will encode a digital value on it. So when the microphone sensor picks up the digital value, it will indicate, based upon that value, whether or not the value was derived from this modulated light signal that was purposefully sent to it. And we can adjust the amplitude, the width of the pulse, and the frequency, or how often the duty cycle. That's called pulse width modulation. And the voltage, so when we turn it on and it's making the pulse, that height of the amplitude, the voltage, that's going to remain reasonably constant. So we don't have to worry about amplitude variations from the source. And we're going to pick a particular frequency that we're sending this pulse signal out, as it's got to be well above the floor level, like the noise level, and it's got to be well below the peak so it doesn't get clipped. So that would be something in the 20 hertz to 10 kilohertz range. And the frequency that we've chosen is 3.141 kilohertz. It's deliberately near, but not exactly, pi kilohertz. Now that was purposefully selected as it's an oddball number. It's a very discernible number, but you also notice that it's a truncated version of pi. So you know it's your signal and not some stray thing. And then the width of the pulse is 71 milliseconds, which if you see that in the signal, you'll know that's what we purposefully sent, because 71 is a prime number. It's not a small prime number, so it's got some muscle to it, but it's not a huge prime number, so it's not overly wide. It's easy to detect. So here's the rig. I have the parts for the rig. I haven't assembled it all yet and fired it up, but I've done this sort of measuring in the past. The source of the photons is a NeoPixel LED RGB. I can adjust the colors. And the force detector is our MEMS microphone sensor. And I'm going to be using one of my favorite Raspberry Pi single board computers to modulate the signal and to detect the audio force, and then be able to produce the results. The interesting thing is it has to take place inside the vacuum chamber. So in the vacuum chamber, everything you see in that sort of tan, the rounded edge box, all of that has to go in and operate under vacuum. So the computer and sensors and detectors and stuff like that all have to run off of a single battery source. And then the sensors for the force detector and the LED emitters, all that's going to be inside the vacuum chamber. But how will I control the computer? How will I know what its measurements are? This particular kind of Raspberry Pi supports Wi-Fi. So I will be communicating through the aluminum wall and the glass lid of the vacuum chamber using Wi-Fi. As I don't have any keyboard or mouse or graphics display, because I don't want to drill any holes through my vacuum chamber, that'll be on the outside. And as I said, I'm not going to be drilling holes through my vacuum chamber. That's a no-go. Everything has to operate under a vacuum on battery power. And I'm going to be controlling it through a shell interface, command line prompt type of thing via Wi-Fi. No keyboard, no mouse, no HDMI display, and no Windows or GUI. I'll be controlling it from my laptop, which has a display, keyboard, trackpad, mouse, that kind of things. But the actual computer, the Raspberry Pi, won't. So how am I going to get all these bits and pieces to work? Well, the Raspberry Pi has an I2S interface to connect to the MEMS microphone. And I'm going to be using Adafruit, which is a website that sells all kinds of electronic things for do-it-yourselfers like myself. And I've already got the NeoPixels. They're really cute. They're 1.5 millimeters by 1.5 millimeters. Tiny, but god-awful bright. And I have the MEMS microphone interface, so I have to hook that up. So I'll be using the drivers, the library, to talk to it via Python. And then I'll have a Python script that will go in and command the interface to modulate the photons and send the test sequences, and then measure the digital sensor response, and then display the numbers of the results. And whenever I change the color of light being sent, I can put like a display break and then put the numbers associated with the results. So I can say, when I did this, it returned that. Whenever you're trying to decide, does it do it or not, then you want to have a very sharp, discerning effect. And I said, well, the best way to do this will start with white, or sort of white. meaning the red, green, and blue channels are at maximum. And then we'll switch from white to blue, meaning red and green are completely off and blue is at maximum. And then green, same thing. Red is off, blue is off, green is at maximum. And then red. Red is at maximum, green and blue are off. And that way, when we get the signal back, we can know it's this because it's such an exaggerated effect. Here's something that you had to think about for a moment, but it makes sense. If the photons are coming out vertically, like I mount the microphone sensor up high and I mount the LED on the bottom and I send the photons up to the sensor, or I do it the other way around. I send the photons down to the sensor. Well, anything that is moving the vacuum chamber is going to cause vertical vibrations, be it vehicles driving by my house, me walking around in my house, or bumping the table that the vacuum chamber is on. So how would I negate that? And it turns out that there's a lot of other things that happen besides the most obvious ones, because I'm measuring things at such a very tiny level. The ground gravity, subsurface ground gravity, water flowing in the Floridian aquifer. If I did this out in the northwestern part of the US, magma flowing around in underground lava, or just the wind blowing. If you get a lot of wind, you ever notice how if you get enough wind that your house might creak, if you have an older wooden house? Same sort of thing. And what about the larger effects of, okay, the sun and moon angle and distance? If the moon can make huge volumes of water rise up as the tides change twice a day, then maybe that can affect these smaller values. So let's do this after dark when the moon's not up. And instead of having it arranged vertical, let's have the rig arranged horizontal so that the photons come out and move horizontally to the microphone sensor. Isolates a lot of those effects. So in summary, radiation reflection pressure transfers momentum, and maybe we can detect that digitally. And if it's quantifiable as a color difference based upon the force difference by the wavelength, then we have a new way of measuring color that doesn't require lenses on top of pixels. It just requires a whole lot of little piece of zinc oxide, a new way of making a color camera. I looked at, trying to get a nanonewton torsion measurement scale, and those things are fairly complicated and cost a lot of money. So I said, let's see something simpler. I can numerically control a NeoPixel RGB LED, and I've got a MEMS piezoelectric microphone circuit. Hopefully it's sufficiently sensitive, but won't know until we try. Had to learn everything possible about NeoPixels and MEMS microphones. And I'm going to have to write some Python code to encode the signal and then swing the parameters quite wide in order to say, it's the signal I sent, not some random thing, and then adjust the color swings quite wide to see if we have measurable, detectable color effects, and then set the rig horizontal so it gets rid of some outside effects. Now, was it verified through observations? I don't know. Wait for part 2, because I'm just getting started. And then if you want to know about the International System of Units, and then how different colors have different nanometer wavelengths, and the low end, the low energy end, infrared, well, radio is actually below that, which is even lower energy, but we'll just keep it to the sort of visible stuff. Ultraviolet being the top end, the highest energy. And then what is this thing you called a Planck constant? And then the definitions of newtons as a force and joules as an energy and Pascals as a pressure. And then devices. And how do you convert a photon force in Pascals to a sound pressure in decibels? Weird calculations. And then when I shine an LED, how do I know how many photons are coming out of it? A lot of them. I know, lots of numbers, lots of physics, lots of, oh, it hurts my head kind of stuff. But I wanted to get it out there to the public, and this is the avenue for doing it. Comments? Questions?
Looking forward to seeing the device work.
Me too. I've worked with NeoPixel LEDs, and I've worked with a MEMS microphone to just do audio stuff. So it's a matter of, is the sensitivity sufficient? If it's not, then I do have microphone transducers. This is a little metal disc that has about a 3/4 inch diameter circular disc of zinc oxide. And they're large microphones. So whenever you see one of these large electret microphones, this is the element that would be inside of it. But that doesn't produce a digital signal. That just produces an analog voltage out. And then you have to have another analog to digital converter and amplifier on the back end that is going to be more sensitive. And I may have to resort to that, but I won't know until I try.
Can you have a part 2 in like 2 months to just let us know the updates as to what you've done and where you're at if you have not completed what you wanted for finalizing it?
Yes, you'll know by next Saturday. If you see a part 2, then eureka. If you don't see a part 2, then I'm either still occupied building and producing observations and deciding whether a MEMS microphone is sufficient, or I have to go to an analog microphone. So I'll keep you updated with progress. But yeah, I don't have the data yet. I got the bits and pieces, but just didn't have enough time this week to put it all together.
Okay. Something to look forward to.
Hold me accountable. Yes.
Yes, that's what I'm doing.
Okay. You do that. That's why I have an audience. You know, I could be like one of these other content creators on YouTube and just spout diarrhea and then put it out there and wait for the irritating comments. But I do it live. I let people actually comment while I'm doing things. Any comments or questions before I stop recording? You hear me? Nothing?